Hi, I'm Aishwarya. In this video, I want to take you through the research paper that I recently published and got accepted in two ICCV workshops held in Honolulu, USA this year. Uh, the paper is titled Vision Language Models Display a Strong Gender Bias. And what I want to do today is to explain the idea in the paper from the very beginning without assuming that you already know what a vision language model is, or what embeddings mean, or what cosine similarity is. I want to make sure that anyone who watches the video, even if they are not from a machine learning background, can still understand why we studied this problem and how we designed the methodology, how the measurements work, and what research tells us about the behavior of modern AI systems. So let us get started. What are vision language models? Before we start talking about the study, let me first explain what a vision language model or a VLM is. A VLM is a machine learning system that can process both images and text. And instead of processing or treating them separately, the model learns to bring the image information and text information in a common embedding space. We can call this common embedding space as a shared representation space or a shared mathematical space. And in this shared mathematical space, similar concepts will stay close together. For example, if I show the model a picture of a cat and there is a word cat, then the picture and the text, they are meaning the same. So words and images, the objects with similar meaning should stay closer in this shared representation space. So if there is the image of a cat and the text cat, then a vision language model should learn to place these two items closer together in its internal representation. So this combined space allows the model to do so many things, like retrieving the right image based on a text query, or describing an image in words, or classifying the objects if there is no training data, or performing zero-shot learning. There are many tasks that a VLM or a vision language model can do. And one of the most widely used vision language models is a clip vision language model. A clip uses two encoders, one for images and one encoder for text. And these encoders convert the images and sentences into mathematical vectors. These vectors are always normalized to have a length of 1, and once they lie in the same space, the similarity between an image and a sentence can be measured using cosine similarity. This cosine similarity tells us how close or far two concepts are inside a model's mind. So modern AI systems are trained on vast amount of data collected from the internet. The internet contains real world patterns, but sometimes this can also contain stereotypes and inequalities. It can contain social biases or gender bias. So why it can contain the stereotypes or gender bias? It is because these models learn statistical patterns directly from the data. They absorb some of these biases also. So if these biases gets encoded inside the model's representation space, then the future systems built on top of these embeddings may behave differently towards different demographic groups. So the main challenge here is that many of these biases cannot be detected simply by looking at the accuracy numbers. A model may achieve good accuracy while it can still show bias in the underlying geometry. For example, if we have a common embedding space like this, we have the image embedding of a female face, we have the image embedding of a male face, there is text embedding for the word cooking, and there is text embedding for the word CEO. So If the model unconsciously places the embedding of the word CEO closer to male faces and embedding of the word cooking similar to female faces, this may reveal a subtle association pattern that does not appear in a typical classification metric. Right. So that is why we wanted to measure these associations directly from the embedding space. That is the main goal of our study. The central aim of our paper is to examine whether modern VLMs associate certain activities or occupations more strongly with male faces or female faces. So we do this by comparing the embeddings of text statements with embeddings of male and female faces. So if the text for an activity sits closer to male faces, then the model implicitly is associating that activity with men. And if it is more closer with the female faces, then that activity is lying more closer to female faces or women. Then we also try to find out the strength of this bias. So strength of this association or this bias can be measured mathematically and it can be analyzed. So to perform the study, the first thing that we needed was a data set. So we collected 220 face photographs as the first data set, and out of these 220 face photographs, 110 were perceived as male faces and 110 were perceived female. We call them perceived because our study does not involve biological or identity-based gender, but the visual impression of gender from the image. Each face, each face region without background or accessories is considered because that might influence the model. And the second dataset that consists of 150 short statements and 150 short statements that cover six categories. Six categories like technical labor, professional roles, domestic labor, emotional labor, cognitive labor, and physical labor. So the objective is to keep the wording neutral so that the model's associations are not influenced by the phrasing, but it is just influenced by the underlying concept. And we evaluate our vision language models, and how we conduct this evaluation is we take two transformer based models, VIT B32 and VIT L14, and we also consider two convolution based models. So the reason for choosing these models are that they are common clip style encoders and they represent different architectural families. So transformers rely on attention mechanisms and capture global relationships, while convolutional networks capture more social or more local information. Using both gives us a broad understanding of how biases behaves across different architectures. Before we compute the embeddings, all images are resized and center cropped and normalized according to model's requirements. And each text statement undergoes tokenization and embedding through the text encoder. To prevent sensitivity to some wording, each statement is expanded into a small set of neutral templates. For example, if a person performing X, an activity involving X, or an occupation related to Y, the embeddings from all the templates are averaged to create a single stable vector for that statement. Now, if you ask me how we compute the association score, let us go step by step into the core mathematical idea. For each statement, let us call it text embedding T. Let VM be the set of male face embeddings. We compute the cosine similarity between T and every vector in VM. And Then we take the mean of these similarities. This gives us how close the statement is to the male group. And we repeat same with the female group and compute the difference. If the difference is positive, then that means the statement is close to male faces, and if the difference is negative, then that means the statement is closer to female faces. So the difference is the bias score. First, we calculate the cosine similarity of the male faces, and we compute the cosine similarity of the female faces, and we find the difference to calculate the bias or the bias score. Now, if you ask me why this cosine similarity matters, why we are choosing to calculate the cosine similarity, this is because all embeddings are L2 normalized and cosine similarity becomes the same as a dot product. This removes the effect of vector magnitude and makes the comparison stable and interpretable. And to explain this in this visual, with the help of this visual, if the angle between two vectors, for example, here we have a female face embedding, female image face image embedding, and there is the text embedding for a word. So these vectors will be having an angle in the shared embedding space. So if the angle between two vectors is small, then this means that cosine similarity is high, which means model considers two concepts to be related. And when this angle is very high, it means the cosine similarity is very less, and the model treats the two concepts as unrelated concepts. And a single measurement cannot tell the whole story. So we want to know how reliable each measurement is. For this, we use bootstrap resampling. We repeatedly sample the face gallery with replacement and we compute the bias score, and then collect the scores across many such samples. This gives us a distribution, and from that distribution, we compute the confidence interval. So if the confidence interval is narrow, it means the measurement is stable, and if the confidence interval is wide, it means the measurement has uncertainty. And in addition to this, we need to know how much bias could appear by a random chance. So for this, we create a null model. We mix all the face embeddings together, randomly split them into two groups of same size, and treat one as a male group and other as a female group. So even though these groups contain mixed genders, we compute the bias score now. So it should be close to zero. The bias score now should be close to zero. And repeating this many times gives us the baseline noise level. And if the real bias scores are clearly above this baseline, then it means that the model's associations are not accidental. It certainly has a gender bias. This was the main idea of our study, and the results that we got are surprising. It surprisingly shows us that all the vision language models, whether that is transformer based or convolution based, it has a clear gender bias, and the VLMs display a strong gender bias. So let us see the results. When we compare the observed bias to the null baseline, all models show gender bias, very strong gender bias that it is very clear. So here is the observed versus null model bias. So if the ratios are greater than 1, then it indicate bias beyond chance. So here we have the results. So when we compare the observed bias with the null baseline, all models here show strong bias than what randomness would produce. And the transformer-based vision language models, VIT-B32, shows the highest ratio of the observed to null bias. And the convolution-based vision language models, the ResNet 50 and ResNet 101, that shows that also shows bias, but slightly lower compared to the transformer based ones. So this suggests that the transformer based models capture more gender related association than the convolution based ones, and this can be possibly due to greater capacity and global attention mechanisms. Now, when we analyze the different categories, some some more patterns emerge. So here we have the different category level bias. So when we analyze these category level bias, it clearly shows that domestic labor shows a strong male associations in many models, and professional roles and physical labor also lean to male. On the other hand, the emotional labor, cognitive labor, and the technical labor, they lean more to female side. The technical labor observation was actually unexpected because many technical roles in real life are male dominated. This mismatch suggests that the internet data used to train these models may carry soft patterns that differ from the real world. So, this was actually a bit surprising, but it was very clear that the domestic labor and physical labor that actually there is bias in the society, and in vision language model also that bias is very strong, whereas in the emotional and cognitive labor categories that is leaning more towards the female side. Now I also wanted to get the statement level examples. So when we study the top biased statements for the transformer based ones, firefighter, carpenter, and truck driver are strongly associated with the male faces, and the words nurse, the occupations nurse, teacher, caregiver, school principal, those are associated more with the female faces. These results align with common stereotypes present in text and image across the internet. Now, other models show similar trends with slight differences. So here I have the result of transformer-based VLMs, but it is also clearly present in other VLM models also. And the presence of such associations inside a model embedding space can influence downstream applications. Even if a system does not explicitly predict gender, the way the embeddings are distributed may cause indirect effects. A retrieval system, if we are using a vision language model for retrieval, then that retrieval system may surface different images for same query depending on the hidden associations. A captioning model may describe people differently. Decision support systems may rank or highlight items differently based on these stereotypical associations that arise from the embedding space. And coming to the limitations of the work, one limitation of our work is we focus on binary perceived gender. So true human identity is far richer than this. So future studies should investigate on the binary representation, race, age, and other intersectional dimensions. So the main goal of our study was to study the gender bias associated in vision language models and see whether vision language models display a gender bias. And our results say that vision language models, especially the transformer based vision language models, display a very strong gender bias. Now, another direction is to explore the mitigation strategies such as modifying the embedding space or using counterfactual augmentation to reduce the bias. So I want to summarize this paper. This shows that modern vision language models do indeed display measurable gender bias in their embedding geometry. And these associations arise due to patterns in the training data and they persist across multiple architectures. Our methodology is actually very simple and reproducible one. And it provides a structural Our methodology is actually simple and transparent, and it is reproducible. And it also provides a structured way to audit multimodal models. As these models enter more sensitive applications, understanding their internal behavior and it becomes very important that the systems we build can be fair and responsible. This is a brief about this paper, and I'm collaborating with people on vision language model research. If you are interested in collaborating with me on VLM research, do check out our website, togolabs.ai. We have a research collaboration program. We have a VLM research bootcamp where I'm collaborating with passionate people on VLM research. And thank you for watching this video. I will record a detailed walkthrough of the paper, and I'll also make a separate video where I explain the code and demonstrate how to reproduce the results. So do let me know your thoughts in the comments and stay tuned for more videos.